All right, we're back and we're a little skewed here. I'm not quite sure why. We'll do the best we can do. Second example, I want to know, why does the car have a spoiler? Obviously, to go really fast. So what does the spoiler do? The spoiler is actually just a wing, but in reverse. A wing causes the plane or causes lift. The spoiler causes lift, but we'll call it negative lift to keep the car down to the ground. So I made up some problem about, let's say a car has a mass of 600 kilograms. Let's say you're trying to take a turn that has a radius, right? A curve is just part of a big circle. So we'll say that this curve has a radius of about 100 meters, and the coefficient of static friction between the tires and the road are 0.75. Don't be confused by that. I know the tires are rolling, but every moment that tire's on the road, that section of tire isn't moving. That's why it's static friction. This is what keeps our car on the road. I want to know, as the car is making this turn, if the car is going 28.6 meters per second, what is the force that I'm calling this lift force generated by that spoiler to keep the car down to the ground? So here I have my sketch of just the car turning. I have identified this force, the frictional force, and now I'm looking at my free body diagram. The free body diagram, I have a normal force in the up direction. My frictional force, static friction, is coming here, what I've labeled my y direction, mg, and if you can't see it, I'll put this here again. What I just drew there in blue is my lift force. So I have this, again, haven't identified anything new. I'm going to use my coordinates that I've defined, x and y, break it into components. Some of the forces in the x direction, some of the forces in the y direction. F equals ma in the x direction. I know my only force here looks like my frictional force. Friction is equal to mass times acceleration. That should be a vector, that should be a vector. I know my frictional force, Fs, is equal to mu, coefficient of friction, times the normal force equals ma. And at this point, I can say, hey, this is a centripetal force. I'm identifying my frictional force as that centripetal force. So I'm going to sub in my centripetal acceleration of v squared over r. So now I have this sub-equation of mu times the normal equals mv squared over r. Stuck, nothing about lift. Let's go to the y direction. My y direction, I have all of these forces. F equals ma. Again, a is a vector. Make sure you vector those. Looking at my free body diagram, the normal in my positive direction minus my lift force minus my weight, or my force through gravity, or mass times gravity, I know equals 0. It's not going up or down in any fast motion. So I bring this to the other side. I can see my normal is my lift force, hey, that's what I'm looking for, plus mg. Sub in normal for normal. Bring that over here. I have my friction, my coefficient of friction, mu, times my lift plus mg equals mv squared over r. Again, this is why we keep things in terms of variables. I can simplify, bring this to the other side, factor out an m. I'm left with a lift of my mass of the car, v squared over mu coefficient of friction times r minus g. Sorry, that was a mouthful. In terms of numbers, once I'm done, I can get a lift of 664, or that negative lift, keeping the car down, of 664 newtons down. Here's a little sidebar. Sorry, if you don't want to watch, feel free to fast forward to the last part. This got me thinking, can I drive fast enough to get my car to drive upside down on, say, a tunnel in a tunnel in Boston? So I started looking some stuff up and having some fun. In order to get my car vertical upside down, that drag force, I have to push the car up to the roof of the tunnel, which means that drag force, or lift, not drag force, I'm sorry, that lift force has to be at least equal to 5,880 newtons. So I'm looking to generate an FL, a lift, of anything greater than or equal to that. We just saw that lift is proportional to velocity. So, knowing that my lift force is proportional to velocity, I looked a couple things up, something we'll get to later in the year, but I know that air resistance has a lot to do with shape. This formula, my lift formula, is 1/2 CL. This CL is the coefficient of friction through the fluid. It's generally based on a few things. There's shape involved, there's velocity involved, there's what it's going through. Typically, this is an experimental find. Rho is the density of the material we're going through, v is obviously the velocity, and a is the area of the thing that we're going through, so the area of my wing. The drag coefficient, because we have lift, we also have drag, is pretty much the same equation. It's an identical equation with the exception of this CD. This is my drag coefficient. That's my lift coefficient. So there is obviously something, and it's not that obvious until I say it, called a lift to drag ratio. If I go too fast, there'll be too much drag. If I go too slow, I don't have enough lift. So we need the right velocity in order for all of that to happen. So the lift to drag ratio is just comparing how much lift I get compared to the drag force we're responding. Lift to drag is equal to or proportional to my coefficients. Do some substitution and some work. The minimum lift, in other words, to get this value, a minimum lift value, divided by some known value. I just got a known value. How fast I need to go, how fast that value was. So plugging in my numbers, 5,880, that's my minimum, divided by 664, that's what I had earlier. My velocity that I'm looking for, v squared, I'm not sure if this is coming up, v squared. Little bit of math rearranging, we get a velocity, sure, it's possible. About 85.7 meters per second, roughly 190 miles an hour. So it is theoretically possible. I may have taken some shortcuts. Feel free to do some Googling and check it. But for those of us who aren't that geeky, hopefully we're back on track to banked turns. Banked turns are really the pinnacle of circular motion. A banked turn, and this happens in real life, the reason we have banked turns on racetracks, banked turns on highways, are because it limits the friction needed to make that turn. So questions can be phrased of what is the angle required to make this turn at 45 miles per hour or 27 meters per second. If something is going so fast, what is my angle? Basically, we can even eliminate friction entirely. Is it possible to make this turn with zero friction? So let's find out. Here I have my banked turn. Notice I have, again, no numbers. I have my car making this turn. I know there's some force. I'm assuming it's friction, but we're going to minimize that friction, which is why I don't have it labeled on my sketch. Now, one thing, every time we have something like angle, we've had this crooked axis to match my angle. We can't do that here because the radius of curvature is measured parallel to the horizontal, not parallel to my incline. So that makes it a little bit more complicated. This is not a true free body diagram. I'll identify everything on the free body diagram. The free body diagram, real forces, should only be what I have drawn here in purple, the normal force and mass times gravity, the weight of the object. Everything else are components or total forces. I know that this is my axis that I'm working with, so I know that mg obviously fits onto it, and I know I need to break the normal this time into components. So I'm not sure if you can see it. I'll put them out here again. That's my y component, Fy. Here's my x component, Fx. And by inspection, I can see that my y's are going to cancel. I'm going to have some net force into that x direction. That net force is what's going to cause that circular motion. So that is what I can identify as my centripetal force. Now we're going back to doing everything how we've always done it with Newton's laws. F net equals ma in the x direction. Fx is mass times acceleration. I've identified the x direction as my centripetal force, so I can sub in v squared over r for my acceleration. And I know through simple trig that Fx, my x component of the normal force, is the normal times sine theta. So I know in my x direction, I have normal sine theta is equal mv squared over r. And again, I'm stuck. Go to the y direction. Same thing, Fy equals ma. My y component is just Fy, which is the normal times cosine of theta, minus mg. I know it's not accelerating up or down, equals 0. And I know it's not accelerating up and down because it is the perfect speed. If it's going too fast, going to fly up the ramp. If it's going too slow, it's going to fall down the ramp. Again, we're eliminating friction. So it's going the perfect speed to stay right there. I know there's no acceleration. That means the normal equals mg divided by cosine theta. Again, very important that we keep things in terms of variables. Sub in my normal for my normal. Mg cosine theta times sine theta equals mv squared over r, and bam. I don't care about mass. So this equation will be good whether you have a semi-truck, a motorcycle, or a bicycle. All of that is going to be the same. So I cancel out my mass. I have g cosine theta times sine theta equals v squared over r. Sine over cosine is tangent. Rearrange, I get a minimum velocity in order to have no friction of the square root of the radius times gravity times tan theta. That's all I have for you today. I went a little long, but we got to geek out about driving on the ceiling. Please like, click, and subscribe if you're on my YouTube channel, and keep your questions coming. Thanks. Have a good day.